Given the graph f of x equals b to the x where b is greater than 1, draw the inverse and state the domain and range of both. What I should say is draw it and the inverse. Alright, so if we have b to the 0, we have 1. We have b to the first power. We don't know exactly what b is, but we'll just say, we'll call that b. If we have b to the second power, that's going to be b squared, something like this. And if we have b to the negative 1, that's the same as 1 over b. And if b is greater than 1, 1 over b will be less than 1. So our graph looks something like this. Our points there, and we can connect them. Now, what's the inverse? Remember, the inverse is a reflection about y equals x. Every point that was on the graph is going to be switched. So if we have, when we look at our graph, we had, looking at a table of values here, xy equals b to the x. And so we had 1 over b, and 0 was 1, and 1 was b, and 2 was b squared. Well, now we're going to switch those, and so when we plug in b squared, we'll get 2. When we plug in b, we get 1, and we plug in 1, we get 0. And we plug in 1 over b, so some fraction, we'll get a negative number. So we don't know exactly where this is. I'm just going to throw it somewhere around here, and I'll call this thing b. And then over here we'll say is b squared. It's just really is to have this idea. So we have for f of x equals b to the x. Well, we can raise b to any power, so the domain will be all real numbers. Let's remember how to write this. X is an element of the set of real numbers. What's the range? When we look at this, what kind of numbers do we get out? We're getting out only positive numbers. There's no way to raise a positive b to any power and get 0. So y is greater than 0. Now what? What is the inverse? The inverse is going to be the exact opposite of those. And so the domain will be x such that x is greater than 0. And we can see that here. It's always on the positive side. And the range, though, will be all real numbers. And you can see that as well. This arrow is going up, 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 and this arrow is going down, down, down. What is this called? Do you remember what this is called? This is called a logarithm. And so that is actually our title. I wanted to go through this first. This is logarithms. So let's take a look at what we have here. This is called, if we say log of x equals a, right here, this log means log base 10, which is also called the common log. When there's no number written at the bottom of the g, it's not at the same level as the g at the bottom of the g, what that one is called is a common log. And it says log of x equals a if and only if 10 to the a equals x. Now, what is, when we look at this, what does if and only if mean? We could take a moment to refresh ourselves. If I say a if and only if b, this goes back to geometry. It means if a is true, then b is true. And it also means if B is true, then A is true. So it means you can go both ways. So if I have 10 to the A equals x, that's going to be this. I can transform that into log base 10 of x equals A. Now, what is a log? A log is an exponent. Let's write this. A log is an exponent. So when I have this thing and it says this log equals A, that's telling me the exponent is A. So the base of the log is also the base of the exponential. So the base to that exponent is going to equal the argument of the log. In general, don't quite have enough room here. In general, log base B of x equals A. And another way to write if and only if is a double arrow like this. Now, what's the base of this? We have a base B. B to log is an exponent. B to the A equals x. So this gives us a way to transform any log or exponential into the other one. Now there's a special base, and the special base is E. So what we get on there is log base E of x, and this is written, this is the same thing as writing natural log. That's what ln means. It's French, and it stands for, if I actually had a French accent, log naturel. So if we have this, we could say ln of x equals k if and only if what? Well, what's the base of the ln? We have to recognize as soon as we see ln, the base is e. So it's e, and log is an exponent. So k is our exponent. E to the k equals x. I threw k in there just so you could see something other than a. What do you know that is logarithmic? Well, one thing we should all know in California is the Richter scale. When we say there's an earthquake of magnitude 6 or earthquake of magnitude 7, they'll always hear that the magnitude 7 is 10 times stronger than a magnitude 6. Why? Because we're talking about an exponent, so we're talking about 10 to the 6th versus 10 to the 7th. What do you do in chem? Your pH scale. And another one that you could deal with is loudness of sound when you're talking about decibels. All right, let's do a bunch of problems. These are basically skill problems, and let's just see about how we can go about doing them. I see log of 10. What I'm going to do is set this equal to a variable, and I always want to see that you've done that. What's the base of this log? The base is 10 to the x equals this 10. Well, what is x here? X is 1. Let's see about this one. Again, we have a log base 10. It's not written. This is our common log, but it gives us 10 to the x equals 1,000, which I want to see that you're writing it as 10 cubed. I want to still work on the fact that we have two bases. Two exponentials are the same with the same base, so therefore their exponents are equal. Now you could skip this first step, and that's okay. 10 to the x equals, how do we transform this one into 10 to a power? Well, we're going to go 1, 2, 3, 4, so it's 10 to the negative 4th, so x equals negative 4. Let's see a couple problems with different bases here. Set it equal to x. We have 5 to the x equals 0.2. Now, at first glance, this might seem, what do you do now? Well, if we take that same hint that in terms of the idea we did in problem 2, and we think of what Polya would say, can we put it into a similar form? These were easy because they had the same bases. Can we make this the same base? Well, 0.2 is the same as 1 over 5, which is the same as 5 to the negative 1. So x equals negative 1. We have two exponentials the same, equal with the same base. Over here, set it equal to x. 5 to the x equals 5 to the, remember the fourth root would be written as a 1/4 power, so x is 1/4. 5 to the x equals 1 this time, so what does x have to be there? This one will allow you just to look at it. X has to be 0. Remember, as long as the base is not 0, any number, non-zero number raised to the 0 power is 1. And we're going to start getting a little bit more complicated as we're going through this. We'll get 8 to the x equals 2. So now we have to look for a same base. We can have a base of 2 because 8 is 2 cubed. So 2 to the 3x equals 2. 3x equals 1. X equals 1/3. Set equal to x. So we have ln. Actually, let me just start transforming it. We have e, the base of the natural log, to the exponent x equals 1 over e cubed. And that can be written as e to the negative 3. So x equals negative 3. And the next one, 7 to the x equals 1. It's just like the one that came above it. You just want to be thinking about that and make sure that you can deal with that. Now we're going to use the calculator to see what happens here. So we're going to press log. Find the log. It's on 3 keys above the on button. Log. I got to turn mine on first. Log of -7. Remember, it's the negative sign, which is below the 3. And hit enter. And what does it tell you? Notice there that the calculator says error, non-real answer. Error, that's what it's saying. Non-real answer. Why does it say that? What's going on with that? Well, what's happening here is we could look at this a couple ways. We could say that log of -7, we could set it equal to x. Let me move our calculator for a second here. And we get 10 to the x equals -7. What can you raise 10 to get a negative number? There is nothing that you can raise that to, so there is no solution. Recall on the other side, we had the graph of this log function. It looks like this. What was the domain of it? The domain was x was greater than 0. -7 is not greater than 0. It is not in the domain. We cannot find it. When we do the next one, type in, so we could just hit quit or enter. We'll type in ln of 1. ln is right below that log key. Move it up a little bit. ln 1, enter, and that gives you 0. This is just to make sure we can do this. ln of 2, and that gives you 0.69. Now the next one says ln of e. So what you're going to do on that one is type in, hit ln, and notice right above the ln in yellow here, there's e to the x. So we need to press second, e to the x, and notice how it says ln of e to a power. We're going to plug in 1, and then close that parenthesis up, and hit enter, and it gives us 1. There's another way we can do it, but we need to know this key on there, so I'll just use this. And this is 1. Now let's solve some problems. Let's use our transformation. What's the base of the log? The base is 5. What is a log? A log is an exponential. A log is an exponent, and so the exponent is here is 2 equals x, so x is 25. Similarly, we have the base is 7, the exponent, that's what the log equals, is 1/2, and that equals x. And you could say write it like that, or you could write it as the square root of 7. Here, this just says log of x. It doesn't have a base written down. What is that base? Well, like we said earlier, that is the common log, or a base 10 when it's not written. So we have 10 to the exponent of -1.2 equals x. Now you could type that in on your calculator, and if we were only going to 2 decimal places, it would give us 0.06. Now that's the approximate answer. And on this one, what's the base when we write ln, natural log? The base is log base e. So this is e squared equals x. Now that's the exact answer. So if we didn't have a calculator, we'd leave it like that, and we're done. If I said to round it to 2 decimal places, we would write it as 7.39 is approximately equal to x, because that's a rounded. Number 8. Our base this time is x. Our exponent is 2 equals 121. We're going to solve this. We put our plus or minus. X equals plus or minus 11. Now, what do you think about that? Well, you have to remember that when we're dealing with these, the base has to be greater than 0, and the base cannot equal 1. So what that does is it throws out that negative 11 completely, and we have just one answer of x equals 11. Now I want you to go through it always when you're taking that square root, have your 2 answers, and then adjust when needed. Over here our base is x, our exponent is 3 equals 64. Now that is the same as 4 cubed, our cube root, and we know our answer is x equals 4. This time our base again is x. Exponent is negative 1 equals 1/2. Now there's multiple ways you can go about doing this. This is 1 over x equals 1 over 2. And I think we've done this so far this year. If 2 fractions are equal and they're not 0, then their reciprocals are equal. So in other words, x over 1 equals 2 over 1, or just x equals 2. I'm just writing that intermediate step just to emphasize that I'm flipping these fractions. And the last one, x to the 1/2 equals the square root of 6. And I was going to say x to the 1/2 equals 6 to the 1/2, so x equals 6. I could have squared both sides to get x equals 6. Again, there's multiple ways to go about it, and that's it for this lesson.